Hi there, Mr. Sutton bringing you the AB Calculus 415 classwork solutions on advanced related rates. For this problem, we have the volume of a sphere increasing at a certain rate. We want to know at what rate in centimeters per hour is its diameter increasing with respect to time when the radius is 3 centimeters. And then they give us the volume formula for a sphere. So ultimately, we got to keep the goal in mind here. We want to know the rate of change of the diameter at the instant the radius is 3 centimeters. So let's write a formula for diameter. All that we know about diameter is that that's going to be 2 times the radius. So let's implicitly differentiate that. We've got multiple rates of change in this problem. We have a volume rate of change. We have a diameter rate of change. So imp-diffing this, we've got dd over dt equals 2 times dr over dt. So if I know the rate of change of the radius, I could figure out the rate of change of the diameter. It's going to just be twice the rate of change of the radius. Okay, well, how do we figure out dr over dt? For that, we have to turn to the volume of the sphere. We know the rate of change of the volume of the sphere, and we have a formula that relates volume and radius. So we can use this volume information to come up with the dr over dt. Let's start by differentiating this volume formula with respect to time. So that's going to be, let's see, 4 pi r squared dr over dt. That's going to equal dv over dt. And now I just have to plug in what I can and isolate dr over dt. So I know that dv over dt is going to be 6 pi. And then the radius, they told us, was 3, so we can plug those numbers in. So this over here is going to be, let's see, 36 pi. Dividing both sides by that, we've got 6 pi over 36 pi, which comes out to 1 over 6. So that's the value of dr over dt. I'm just going to plug that in over here to get dd over dt. So that's 2 times 1 over 6, which reduces to 1 over 3. And that's going to be centimeters per hour, so that's going to give us answer choice A. On this problem, in the triangle shown, if theta is increasing at a constant rate of 3 radians per minute, at what rate is x increasing per minute when x equals 3 units? So this is a related rates problem. We have the rate that this angle's changing at and the rate that this triangle side's changing at. Let's write a formula that puts them all together. So since this is a right triangle, I can use one of my SOHCAHTOA relationships, sine. We can say sine of theta equals opposite over hypotenuse, so x over 5. And then, depending on how much you know about calculus versus trigonometry, there's a couple ways you could go from here. So if you just want to get theta all by itself before taking the derivative, we could take the arc sine of both sides. So we could say theta equals arc sine of x over 5. And then in differentiating implicitly with respect to time, we've got the arc sine of something, so that's going to be 1 over the square root of 1 minus something squared. So square root of 1 minus x over 5 squared, times, now we need to multiply by the tail of this thing, which is going to be 1/5, because we have a coefficient of 1/5 inside this function, times dx over dt. Because again, we're differentiating with respect to time. So at this point, we're going to simplify things a little bit, and then we needed to solve for d theta over dt, because we wanted to know at what rate. Actually, we need to solve for dx over dt, so we need to plug something in for d theta over dt. So simplifying things, I can write this as 1, or I'll actually say dx over dt over 5 times all this stuff, and I'm going to plug in 3 for x, because that's what x equals at this moment in time. And at that time, d theta over dt is also going to be 3. Theta increases at a constant rate of 3. So here's everything plugged in. We had d theta over dt. X was 3 at this time. And then we're just moving this into the numerator to make it a little bit easier to solve. So this is going to be 1 minus 9/25, which is 16/25. Square root of 16 over 25 is 4/5. 5 times that is just 4. And then if we multiply both sides by 4, we get dx over dt equals 12. So that's answer choice E. Just to rewind a little bit on this one, there was another way to do this problem if you didn't want to mess around with arc sine. So I'm going to still start with sine of theta equals x over 5, but now I'm going to isolate x, whose derivative is ultimately what I'm solving for on this problem. So I can write x equals 5 sine of theta. And now I will differentiate implicitly with respect to t. So this will be dx over dt equals, this is going to be 5 cosine of theta times d theta over dt. And this is ultimately a much easier derivative to take. So there's that. But now if you look at what's going on here, I still need to know d theta over dt, which they told us was 3. But we also need to know cosine of theta, or specifically we need to know theta. So how do we find that? Well, they told us that this is all happening when x equals 3. So we can actually go back to the original equation here and write sine of theta equals 3/5. Now how can we get cosine out of this? Well, there's a few ways to go about this. Probably the most straightforward is to recognize that sine is really y over the radius of some angle on a circle. So we have a y value of 3, we have a radius of 4, or 5 rather, and then if you want to get cosine, cosine is x over the radius, so you need to find the x value out of this. X, y, and r have a Pythagorean relationship. It's x squared plus y squared equals r squared. So we could write x equals the square root of r squared minus y squared, or 5 squared minus 3 squared in this case. So x is then going to have a value of 4, which means the cosine is going to be 4/5. So cosine of theta is 4/5. We can then substitute 4/5 in for this cosine of theta. So we've got 5 times 4/5 times 3. 5's cancel, you just have 4 times 3, which is 12. Again, answer choice E. On this problem, sides and diagonal of the rectangle shown above are strictly increasing with time, so that means they're never going to have a slope of 0 if you look at their rate of change. And at the instant when x equals 4 and y equals 3, dx over dt equals dz over dt, and dy over dt equals k times dz over dt. That's a whole lot of information. We want to know the value of k at that instant, given all this craziness. So let's start with something that ties all of these things together. K is wrapped up in the rate of change of dy over dt. So we need something with a y in it, and we can write a relationship between x, y, and z based off of this. This is actually a right triangle because it's a rectangle. So that means that x squared plus y squared equals z squared, Pythagorean theorem. Now we're going to differentiate implicitly with respect to time for all of these. So this is going to be 2x times dx over dt plus 2y times dy over dt plus, or equals rather, 2z times dz over dt. And at this point, I'm going to go ahead and plug in all the information they gave us. So for x, we have 4. So that's 4 times, well, dx over dt they told us was dz over dt. So it might be useful to make that substitution and see what happens. Next, y, they told us was 3. So we've got plus 2 times 3. And dy over dt, they told us was k times dz over dt. Over here, what's z? I don't know, but we could figure it out. So using Pythagorean theorem, if x is 4 and y is 3, z is going to be the square root of 4 squared plus 3 squared, which is the square root of 25, which is 5. So we're going to have 2 times 5. And then dz over dt, they didn't give us any other information about. But the good news is we've got a bunch of dz over dt's here. So algebraically, we ought to be able to do something to eliminate that as well. Before we do that, though, for my next step, I'm just going to clean things up a little bit. So this is going to be 8 dz over dt plus 6k dz over dt equals, and now we'll have 10 dz over dt. To make my life a little bit easier, it'd be great if I could divide by all these dz over dt's. Now, we're kind of hesitant to do so because we've been told not to divide by variables. The reason we can't divide by variables usually is because we might be dividing by 0. So that means if we're guaranteed these dz over dt's are never 0, we can actually go ahead and divide away. Are we guaranteed they're not 0? Here's where we have to read the problem again. They said that the side and diagonal of the rectangle are strictly increasing with time. If our diagonal is increasing, strictly increasing, that means that it's always going to be greater than 0. dz over dt itself is always going to be greater than 0, which means that it can never be 0, which means that we can actually divide by dz over dt. So if we do that, that's the much simpler equation 8 plus 6k equals 10. And then if we subtract 8 and divide by 6, that's going to be 2 over 6, which comes out to 1/3, which is answer choice B. For this problem, we have this cone-shaped container for some water. We have a radius of 4 feet and a height of 12 feet for this whole container, and we have some water flowing in at a rate of 6 cubic feet per minute. We want to know how fast the water level is rising when the height of the water is at 5 feet. And then they give us the volume of a cone right here, this formula. So we've got different rates of change going on. We're asking how fast the water level is rising, and we're given how much the volume is changing per minute. Since we have related rates going on, we're going to differentiate implicitly with this volume formula. But before we do so, right now we've got two different variables on this side. That's going to create a messy product rule kind of situation with R's and H's and dr over dt's and dH's over dt's. Another way of doing this would be if we could express everything in terms of a single variable over here. Which variable would be better? Since we want to know how fast the water level is rising, if we could find a way to express these R's as H's, and then we just took the derivative, that would make our lives a lot easier. The key to relating R and H is similar right triangles. This is a right triangle here if you just look at this piece of the cone. The water level down here is going to form its own right triangle with its own radius and its own height. But since these are right triangles with a common angle down here, these are going to be similar right triangles, and we can write a proportion. We can say that the radius over the height of the water level is going to equal 4 over 12. And now that we've got this proportion, we're going to go ahead and isolate one of these variables. I want everything in terms of H eventually, so that means I have to isolate R so that I can substitute in for the R in this equation with something else. So to do that, I'm just going to multiply H to the other side, so that's 4H over 12, which I'm just going to reduce to H over 3. All right, now that I've got a way to express R in terms of H, let me substitute back into this equation. So this is going to be 1/3 pi times H over 3 quantity squared times H. And I'm just going to clean this up a little bit. So this is H squared over 9, which with this H gives us an H cubed over 9. The 1/3 down here is going to make that 9 a 27. So when the dust settles, we have pi over 27 H cubed equals the volume. And this is something that's going to be a lot nicer now when we take the derivative. It's time to take that derivative. So on the left side, we're going to have dv over dt. On the right side, multiplying by 3 and reducing, we're going to have pi over 9 H squared dH over dt. At this point, we need to plug in for H and dV over dt. The volume rate of change, they said, was 6 cubic feet per minute. The height at the moment in time that we care about here is 5 feet. So we have 6 equals pi over 9, 5 squared dH over dt. And looking at the answer choices, this is definitely a calculator situation, so let's do that division now. So to do this division in a way that I'm not going to get messed up by PEMDAS, I'm going to do alpha y equals and call up my fancy fraction form. In the numerator, I've got 6. In the denominator, I've got pi over 9 times 5 squared. So I'm going to do another fancy fraction down there, and I'm going to put pi over 9, and I'm going to multiply that by 5 squared, and hopefully we get something that's an answer choice. I get about 0.688 if we round off, and since this is height, this is going to be, let's see here, feet per minute. So that's going to give us answer choice B. For this problem, we have a person 2 meters tall walking directly away from a street light that's 8 meters above the ground. If the person's walking at a constant rate and the person's shadow is lengthening at the rate of 4/9 meters per second, at what rate is the person walking? So this is kind of a tricky situation. We can model it with 2 triangles. So this bigger triangle, this side over here, this is the street light. This smaller vertical line, this is the person. And the shadow of the person goes from here over to the tip of the triangles, the smaller triangle, and then the distance between the person and the lamppost is this right here. So putting on some numbers, this vertical line is 2. That's the height of the person, 2 meters. The street light, they said, was 8 meters. And then we have to represent these distances too, because we've got some rates of change for these. So I'm going to call this distance here between the person and the end of the shadow, this is going to be S. This is the length of the shadow. And I'm going to do another distance over here, which I'm going to call W, which is the distance that the person has walked away from that street light. All right, so how do we make sense of this situation? Ultimately, we want dW over dt, the rate at which the person is walking away from the street light. What are we given? Well, the person's shadow is lengthening at a rate of 4/9 meters per second, so they gave us ds over dt. We've got related rates going on, so we need to write an equation that ties all of this stuff together and then do a little implicit differentiation. What equation could I use? These are both right triangles, and they have a common angle over here. So these are actually similar triangles, and we can set up a proportion. We can say that this side over this side is going to be in the same proportion as W plus S over just S. So we've got big over small and then big over small, proportion with triangles. At this point, let's just simplify a little bit and then we'll implicitly differentiate. I mean, we could do it right now, but it's going to be a mess. So let's see here. I'm going to move the S over here. And before I do any of this, I'm going to reduce this to just 4. So we have 4S equals S plus W. And then, let's see here. Let me subtract S, so W equals 3S. At this point, I'm going to go ahead and implicitly differentiate with respect to time. So this is going to be 3 ds over dt equals dw over dt. And dw over dt is exactly what we're solving for, so this actually worked out pretty well. So we just have to do 3 times the rate of change of the shadow. What's that? Well, that's this 4/9 number they gave us up here. So that is just 3 times 4, so 12 over 9, which reduces to 4/3, and that'll be meters per second. That gives us choice D.